In this lecture, we'll explore how machines interpret text, including vectorization, embeddings, key phrase extraction, and summarization. Vectorization techniques convert text into numerical representations, which are a foundation for understanding structure and semantic of text. Even though they're primarily focused on syntax features, they provide the basis for more advanced semantic analysis. Word embeddings are a direct approach to capturing semantic meaning. They represent words in continuous vector space, where semantically similar words are positioned close together. This approach goes beyond surface-level text, representing to capture deeper meanings and relationship between words. Key phrase extraction involves identifying important phrases that convey significant meaning within a text. So this process is inherently semantic because it focuses on understanding and highlighting the most meaningful parts of a document. And finally, document summarization condenses the document into its essential points. This requires a deeper understanding of the document semantics. Both LSA and TextRank technique aim to capture and represent the most important information and reflect the underlying meanings and themes of text. Vectorization is important in natural language processing as it converts text data into numerical formats that machine learning models can process. We'll cover three primary techniques: bag of words, bag of n-grams, and TF-IDF. Bag of words is one of the simplest vectorization techniques. It involves creating a vocabulary of all words in the text and then representing each document by counting the frequency or occurrence of these words. While it doesn't capture word order or meaning, it sets the groundwork for more complex semantic analysis. Let's see how bag of words works using a simple example. First, let's take two sentences. Sentence 1, the restaurant has great food. Sentence 2, the food at this restaurant is delicious. These sentences will be our input data. Now we build our vocabulary. The vocabulary is a collection of all the unique words in the input sentences. So here our vocabulary includes the restaurant has great food at this is delicious. Notice that each word appears only once in the vocabulary, regardless of how many times it appears in the sentences. Now let's create a matrix where each row corresponding to a sentence and each column corresponding to a word in our vocabulary. We then fill this matrix with the count of each word in the corresponding sentence. And so this matrix is our bag of words representation. Bag of n-grams improve upon bag of words by considering combinations of n consecutive words. This helps capturing the context and meaning better than single words. So for example, New York as a bigram retains its meaning of the New York City, unlike in the bag of words where it separates into the word new and York. Bag of n-grams is a natural extension of bag of words. It's another way to represent the document. An n-gram is simply any sequence of n tokens or words. For example, let's use the following phrase: Nelson's is the best restaurant ever. For the 1 gram or unigrams, each word is considered individually. Nelson's is a gram, is the best restaurant ever. 2 grams or bigrams use pairs of consecutive words. Nelson's is the best restaurant. And 3 grams or trigrams use triplets of consecutive words. Nelson's is the best restaurant, and best restaurants ever. This breakdown demonstrates how n-grams capture sequence of words, increasing context as the value of n increases. A bag of n-grams model has the simplicity of the bag of words model, but allows the preservers of more word locality information where the words locate at. A bag of n-grams model represents a text document as an unordered collection of its n-grams. So in the typical bag of n-grams model, this n-grams in the example will be example from a large number of n-grams observed in a text corpus. TF-IDF balances word frequency with how unique the word is across documents. Common words like the are less significant, whereas rare words are given more importance. So this technique helps in highlighting distinctive words in the document. We'll talk about TF-IDF more in the context of classification models in the later module. Word embeddings provide dense vector representations of words that capture semantic meanings. Unlike traditional vectorization methods, embeddings can understand context, making them powerful for different natural language processing tasks. Understanding semantics in language is all about extracting the intended meanings from complex phrases. It's what allows us to grasp not just the words themselves, but ideas and emotions behind them. Let's take a look at a couple of simple examples. Python is relatively easy to learn. And another sentence is, that was the worst movie I've ever seen. This sentence is straightforward and their meanings are pretty clear. In the first sentence, we understand that the person finds Python, the programming language, not too difficult to learn. In the second sentence, the speaker is expressing a very negative opinion about a movie. However, language can get much more complex and nuanced, which brings us to our next example. I do not dislike green eggs and ham. This sentence requires us to handle negation. It's a bit trickier because we need to recognize that not dislike actually means like, or at least don't hate. So understand these nuances is very important for natural language processing, which where we need to interpret and generate human language accurately. So that's why we use word vectors to represent words in a high dimensional place. That way we can capture the subtle relationships of meaning more effectively. Machine learning helps us understand the meanings behind complex phrases. For example, straightforward sentences like Python is relatively easy to learn are simpler for models to interpret, but more complex phrases such as I do not dislike green eggs and ham requires the model to handle negations and understand context more deeply. Word vectors are numeric arrays representing each word in large corpus. Designed so that words used together in similar contexts have vectors that are closer together. So this approach enables the model to recognize, while it may not be inherently understand what a lion is an animal, it does know that lion and cat are contextually closer than lion and dandelion. Now, training these models can be very time consuming, often take hours or days with extensive data. That's why for most practical applications, we use pre-trained models like those provided by Spacey. So word vectors or word embeddings offers a mathematical way to represent and derive context from words. So for instance, in Spacey, this vector is 300 dimensional. This means each word is represented by an array of 300 numbers. Models such as in Core Web MD are representing as English Core Web Median Dictionary, and the large dictionary utilize the same word-to-vec algorithms, ensuring consistent word vector representations across different model sizes. Word2Vec developed by Google is a popular word embedding technique. It has two models, continuous bag of words or CBOW, predicts the current word from a window of surrounding context words, versus a skipgram does the reverse. It predicts context words given a target word. So this embedding captures the context or relationship between words effectively. Let's see an example. We'll use a small corpus consisting of 2 sentences. I love machine learning, and machine learning is fun. We train a word-to-vec model using this corpus, and the code snippet shows how to train the model and extract the vector for the word machine. And notice how simple it is to get started with the word-to-vec using the Jensen library. The word vectors produced by word2vec are high-dimensional numeric representations. Each number in the vector represents a dimension of the word features. And these vectors capture both syntactic and semantic relationship between words. So that means similar words will have similar vectors. Vectorizing high-dimensional data can be challenging. So we use techniques like PCA or principal component analysis or TSNE or T-distributed stochastic neighbor embedding to reduce the dimensions. PCA reduces the dimension linearly, whereas TSNA capture nonlinear relationships. So here's how we can use PCA to visualize our word vectors in the 2D space. Word2vec has numerous applications in NLP, or natural language processing. It can be used for similar search to find words or documents with similar meanings. Text classification to categorize documents, sentiment analysis to determine the sentiment expressed in text, and even machine translation. The ability to capture semantic relationships makes word2vec a powerful tool in these areas. GloVe is another word embedding technique. It's developed by Stanford. It combines the advantage of global matrix vectorization and local context window methods. It leverages word co-occurrence statistics from a corpus to learn embeddings. It captures global relationship between words that way. Here's an example. In this visualization, we're exploring the semantic relationship between words related to royalty and hierarchy by leveraging Spaces GloVe embeddings and the TSNE dimensional reduction. We transformed high-dimensional word vectors into a 2D scatter plot. In this 2D scatter plot, each point represents a word. The position of these points reflects simplicity between words in the reduced space. So you notice that king and queen are positioned close together in the top left corner, indicating their association as royal titles. Whereas princess and prince are situated in the lower right corner, reflecting their more family relationship. This plot gives a kind of insightful representation of the semantic nuance captured by the word embeddings. And it tells us the intricate interplay of language within the context of royalty and hierarchy. The next example is similar. Here we extend our exploration of semantic relationship to a 3-dimensional space, while maintaining the focus on words associated with royalty and hierarchy. So we use Spaces GloVe embeddings and the TSNE dimensional reduction. We transform the high-dimensional word vectors into a 3D scatter plot. Each point in the plot represents a word, and its position in the 3-dimensional space reflects the similarity between words. Notice that the king and the queen occupies the top left corner, princess and prince situated in the lower right corner, kind of showing their hierarchical relationship. So this 3D visualization also offers a perspective on semantic nuance captured by the word embeddings. Next, key phrase extraction is a process that involves identifying significant phrases that convey the main ideas of a text. This is important for summarizing and indexing documents. We'll discuss two methods, collocation and weight tag-based extraction. Collocations are pairs or group of words that frequently appear together, providing meaningful units. For example, New York or machine learning. Statistical measures like point-wise mutual information or PMI or chi-square tests can be used to identify these collocations. So this output shows us sequence of the 2 and 3 words generated by n-gram along with the number of times they occur throughout the corpus. And we can see that most of the collocation point to the people who are speaking something as said, and we can see that people who are popular character, and this text corpus is Alice in Wonderland. So we can see that the people character in Alice in Wonderland, or people like character, like the mock turtle, the king, the rabbit, the hatter, and Alice, they all show in the collocations. Weighted tag-based extraction leverage parts of speech tagging, or POS tagging, to identify key phrases. By assigning weights to different tags, like giving higher importance to noun phrases and adjectives, we can extract more relevant key phrases that summarize the document effectively. RAKE stands for Rapid Automatic Keyword Extraction. RAKE is simple yet powerful algorithm used to extract key phrases from text. Unlike machine learning-based approaches, RAKE is purely statistical. So it makes it easy to implement and use in different contexts without needing extensive training data. The process begins by splitting the text into phrases using delimiters such as stop words and punctuation. Then RAKE scores individual words based on how frequently they appear and how often they co-occur with other words. So finally, it scores entire phrases by summing up the scores of individual words. One of the key advantages of RAKE is that it's both fast and efficient, making it suitable for processing large text quickly. It also works well across different languages and domains without the need for customization. Let's take a look at an example to see how RAKE works in practice. Here we have a short paragraph about elephants. To extract keyword from this text using RAKE, we can write a simple Python script and where we first import the RAKE from the RAKE NLTK library. Then we can initialize RAKE and pass our text to the extract keywords from text method. This method processes the text and identifies the key phrases based upon their frequency and co-occurrence scores. The getRanked phrases with scores method then returns the ranked key phrases along with their scores. As we can see in the output, phrases like African bush elephant and African forest elephant are given the high scores. This indicates that they're important in the text. This example demonstrates how RAKE can efficiently extract meaningful keywords from a body of text, making it a valuable tool for text analysis. Document summarization is about condensing a document to its essential points. This is vital for a quick understanding of large text. We'll look at two techniques: latent semantic analysis or LSA and TextRank. Latent semantic analysis or LSA reduces the dimensions of the text data using singular value decomposition or SVD. This technique identifies patterns and captures the underlying concepts, allowing for effective customization of documents by focusing on the most important concepts. TextRank is a graph-based ranking algorithm similar to Google's PageRank. It builds a graph of sentences where the edges represent sentence similarity. So by ranking the nodes or sentences in the graph, it extracts the most important sentences for summarization. From this similarity graph, we can see how the sentences of a document are not linked to each other based on document similarities. This graph shows how well connected some sentences are to the others. So we now can compute the PageRank scores for all the sentences and build our summary using the top sentences. And we can specify how many such sentences we want to use. To summarize, we covered vectorization techniques such as bag of words, bag of n-grams, and TF-IDF, which convert text into numerical data. We also explored word embeddings like word2vect and GloV that capture semantic meaning. We also discussed key phrase extraction methods and summarization technique like LSA and TextRank. These tools are fundamental for various natural language processing applications.